In Chapter 3, Section 1, we're going to look at derivatives, but now I'm going to show you all the shortcuts that would have made Chapter 2 way faster. So we're going to teach you some methods to do derivatives in a much faster way than taking the limit as h goes to 0 of the function, adding an incremental h value into it. So let's look at the first problem. It says, differentiate the function 2 raised to the 40th power. So 2 raised to the 40th power is just some number. It's a huge number, but it is just some number. So the first derivative we're going to learn is the derivative of a constant. So if f of x equals any constant, the derivative of that is 0. And here's the idea. The derivative is the slope of the tangent line, if we recall from Chapter 2. So let's say 2 to the 40 is some horizontal line way up here on the y-axis, or in fact any constant. Let's say the constant, let's say it's c, where c equals negative 20. Then we have a horizontal line at negative 20. Well, the slope of these tangent lines at any point is 0. So I can pick any tangent line I want. Slope is 0, slope is 0. Tangent line here, slope is 0. Pick the tangent line here, the slope is 0. So the derivative is slope of the tangent line, so these are all going to be zeros. So that's the first one we have, is any constant, any number, the derivative is 0. Okay, in problem 2, they give us a function. Basically, we have a function where we have some slope times an x value plus some constant. Well, we know the derivative of a constant is 0, so this second term is going to become 0. So that 2.4 will become 0. And it turns out that the derivative of a number times x is just the number. So that's our second rule. Any number in front of x, the derivative of that is just that number. So if I have the function equal to 5.8x plus 2.4, the derivative of this is just 5.8, the number in front of x, plus 0. So the answer would be 5.8. Okay, so actually let's hammer that home a little more. So let me do a bunch of functions. So let's say we have a table of functions and then we'll find their derivatives. So let's start with 1x, 2x, 3x, 4x, 15x, negative 17x, negative 1001x, 12.43x, and 3/2 x. You'll be able to do these derivatives really fast. The derivative is 1, 2, 3, 4, 15, minus 17, minus 1001, 12.43, and 3/2. So I would expect this to take you literally 2 seconds on a test. Derivative of a number in front of x is just that number. Now, this is really a subcase of a more general rule that we're building towards, but for now, you can just kind of memorize this approach, and hence you don't have to memorize, oh, the derivative of 2x is 2, and oh, the derivative of 3x is 3. No, just remember this algorithm of just dropping the x and taking the number. Okay, now it gets a little more complicated when x is raised to a power. So this one has x squared. So I'm going to show you the pattern and we'll see if you can pick up on it. So let's say I have 1x squared, 2x squared, 3x squared, 4x squared, 15x squared, negative 17x squared, negative 100x squared, and 19 halves x squared. Okay, the derivative will be 2x, 4x, 6x, 8x, 30x, negative 34x, negative 200x, and 19x. So what do we do? So we doubled the number in front, and we subtracted 1 from the power. So all these x squareds became x to the first power, and the number in front got doubled. So that's the rule for things being squared. And we're getting very close to building the general rule, which we'll have here in a little bit. Okay, so let's look at this problem. They gave us g of x is 3/4 x squared minus 6x plus 15. The derivative of that is equal to, really what happens is you are multiplying this 3/4 times 2, and then the x squared becomes x1. And we recall from the last example we did that negative 6x, the derivative would be negative 6, the number in front. And we recall that any number becomes 0. So we've used all three rules right there for this one. Now there is a little bit of simplifying we can do. This would be 6/4. We don't usually write x to the 1, we'll just write it as x, minus 6. And we can simplify 6/4 to be 3/2. So that would be the derivative. So we type 3/2 x minus 6. Okay, and so we're building towards our general rule. Okay, now in the next one, what we want is we do want these to be in polynomial form. So we want it to be x3, x2, x1, and a constant, something like that. So if you have this where you have a bubble and x squared, you want to distribute this x squared. So we're going to get g of x equals x squared times 1 is x squared times minus 9x is minus 9x to the third. Okay, we know g prime of x is 2x to the first. So that 2 will multiply into this 1 here and become 2, and the x2 will become x1. But we don't know how to handle x to the third. So I think this would be a good spot to show you the general rule. So let me just pick a few functions and we'll show you their derivative and see if we can figure out the general rule for what's called powers. So we already know what x squared does, so let's start at x to the third, and then x to the fourth, and x to the fifth, and x to the sixth, and x to the seventh. The derivative of these is you bring the power down and subtract 1 from the power. So this is 3x to the second. Bring the 4 down, it becomes 4x to the third. So I'm bringing the power down, and then I'm subtracting 1 from the power. Bring 5 down, 5x, subtract 1 from 5, becomes a 4. 6x to the fifth, x to the seventh will become 7x to the sixth. Now what happens if we have a number in front? So let's say I have this case right here, minus 9x to the third. Well, you still bring that 3 down, but now you multiply it into the 9. So this will become minus 27x to the second. So the rule is, the general rule is, if I have some number in front of x, and I have x to some power, the derivative would be c times p, x to the p minus 1. And we should probably box that. Let me write it again up here. Oops. If my function is a constant times x to some power, the derivative of that function is the constant times the power times x raised to the power minus 1. And this is called the power rule of derivatives. The power rule. Okay, it's the most powerful rule we'll have in derivatives. Honestly, we'll use it a ton. So the quicker you can kind of see this pattern, the better. Okay, so let's finish this one. We brought the 3 into the 9, it became 27, the minus stays, and then this x3 becomes x2. So that's going to be the answer. And notice I don't write x to the first power. I only wrote it there to solidify the pattern, but I don't need it for the answer. Okay, so that'll be problem 4. Okay, so in this one we have a negative power. Now a negative power doesn't matter, the rule is still going to apply. So if we have this function f as a function of r equals 3 over r to the third, well, the first thing I'm going to do is change that to 3 to the r to the minus 3. So we can always take a reciprocal of a function if we make the power negative. So this is a general rule we had before. If you have x to the minus p, that's the same as 1 over x to the positive p. Or you can write this, or you can go either way. So we actually went this way. So you can write this negative powers however you want. Or you can write fractions as negative powers and negative powers as fractions. Okay, so now we're going to use the same rule. The derivative states just bring the power down, so it's going to be 3 times minus 3. Now here's this kick, be careful, and subtract 1. So the power is minus 3, but then the rule says subtract 1. So we're going to get 3 times minus 3 is negative 9, r to the minus 4. So when the powers were positive, they shrank. Power 5 became power 4, power 6 became power 5. But in negative powers, they actually get bigger. So it's, well, more negative. So a negative 3 power is going to turn into a negative 4. But the rule has not changed. We still subtracted 1 from the power. Bring the power down, subtract 1 from the power. So this should be the answer. I'm going to try to type it like that, but they probably want me to write it as a fraction. So actually, let me just probably write it like they want. This would be minus 9 over r to the positive 4. It's probably how they want me to type it. Okay, and we're good to go there. Okay, so that is positive powers, negative powers, an example of each. Then we go to fractional powers. So what if we have the 6th root of t? So they're saying I have some function h, it's a function of t, and it's equal to the 6th root of t minus 6e to the t. Well, we've got 2 things in here I need to teach you. So there's 2 different things. First off, we're going to write this as a fractional power. So this is really t raised to the 1 over 6. Okay, so whatever the t raised to the power inside, that number goes on top, and then the number outside of the radical goes on the bottom. So this is t raised to the 1/6. Maybe I should write that over here. So if I have m root of x to the n, that is x to the n over m. So that's how you write this fractional power. So 1/6 is 1 over 6, and then this is minus 6e to the t. Well, the first thing I have to explain, well, let's do what we can do. So fractional powers are no different. It's still bring the power down, so it's 1/6 times this 1 in front of the t. So it'd be 1/6t raised to the 1/6 minus 1. So you just use the general power rule, bring the power out front, and then subtract 1 from the power. But now how do we handle exponents, or e raised to something? So if we have, let me write this down here, if we have the function some constant times e raised to another constant times x, the derivative of that is c times a e to the ax. So exponent function is unique in that you don't subtract 1 from the power. So this part is going to stay exactly the same. everything stayed exactly the same. The only thing that happened was we bring the a in whatever number's in front of this variable, we bring it out in front. But in our example, the number's a 1, so it's not actually going to change anything. This is going to be 6 times the power 1, and then e to the 1t is going to stay exactly the same. So that is how you would handle exponent functions. Okay, it's actually kind of interesting why that is. So it turns out exponent function starts at 1 when x is 0, and then it goes up like this. This would be e to the x. Well, it turns out that its derivative, I think this is neat, but not a lot of people maybe agree with me. Its derivative at any point is exactly the same as the original function. So the derivative of all these is matching the curve exactly. So if the function is e to the x, its derivative, kind of amazingly, is also e to the x. So the slopes of the tangent lines are exactly the same as the original function. Kind of a neat result. Okay, but we just have to clean up our problem a little bit. So we have to figure out how to take 1/6 minus 1. And so we're going to get h prime of t is 1/6 t to the 1/6 minus 6 over 6. So change 1 to a denominator 6. This is just going to be 6 times 1, which is 6, e to the t. And all we have to do is write this as t to the negative 5 over 6, because you have 1 minus 6 is negative 5 over a common 6. And I'm going to see if they're going to let me type that in. No, I bet they won't. So let me write what it's going to be. The 1's going to go all by itself. The 6 is going to come down here, and this is going to become the 6th root of t to the 5th. Okay, so what happened? I got rid of the minus exponent by putting the entire t function, the entire t variable in the denominator next to this 6. And I rewrote it using this rule over here. So I made it, the 5 goes with the t, and the 6 of the denominator goes as a 6th root of t. So I'm betting that's what they want me to type in. So let me try. Okay, and you can see that I have it correct. 1 over 6 times the 6th root of t to the 5th minus 6et. Now, you do have to, when you click in these boxes, you get these buttons over here on the right, and you have to go to functions to get this button here for the 6th root of t to the 5th, and then you also have to get this button here, e raised to a power. So you'll use these buttons over here to get that done correctly. Okay, so let's look at problem 7. Okay, so this one's offering nothing new. It's just more practice with the exponent function and fractional powers. So what do we have? So we have y equals 2e to the x plus 4 over the 3rd root of x. And there's really a 1 on that x. So y, I'm going to rewrite this, is 4x to the minus 1/3. So I can rewrite the radical as a fractional power, 1 over 3, and I can write x next to 4 by making that power negative. So I basically flip it to the top. Now we can do our derivatives. So the derivative of 2ex is just 2ex. Doesn't change at all. This one, however, the minus 1/3 is going to come down and multiply the 4, and then we are going to subtract 1 from that power. So we're going to get 2ex minus 4 over 3, and then this is going to be x to the 1/3 minus 3/3. And that's going to be minus 2/3 when you subtract 3/3 from 1/3. In the last step, let's write it exactly how it should be. It's minus 4 over 3 times the cube root of x squared. Okay, so that's getting this negative power by writing the x in the denominator, and then the 2 stays with the x and the 3 goes outside the radical. So this should be the derivative. Okay, I did have a mistake here, but I caught it. So let's look at it. Right here on line 1, 2, 3, 4, I forgot that this original 1/3 power was negative. So that's going to be negative 1 minus 3, which makes this a minus 4/3, which makes this x to the 4. So I had to put that 4 in right there. So just be careful. I forgot a minus sign on that step, which would have increased the number on top, not decreased it. So it's actually minus 1 minus 3, which is minus 4 on top, which then leaves it x to the 4th in the 3rd root of that. Okay, so that would be problem 7. Okay, in problem 8, it's going to be nothing new, but they're going to use letters. So we don't have numbers now. It's just going to be letters. So it says z of y is a over y to the 6th plus b e to the y. Well, first we're going to change this to be a y to the minus 6, and then b e y we're not going to change at all. Okay, and then the derivative z prime of y would be bring the minus 6 down times the a, and we can write it in that order, y minus 6 minus 1 plus, literally this second term doesn't change at all. So because this is a 1 in front of the y, this would just be b times 1, but it doesn't change it. Okay, so then the last step is to say z prime of y is minus 6a y to the minus 7 plus b e to the y. And that should be the answer for that one. I should have mentioned here there was one more step to get the final answer, and that is to write this back as a fraction. So the minus 6 and the a go on top. The y becomes a positive 7 power now because I'm making it a fraction again. Then the b e y. And that's what I typed in, and that's correct. Okay, problem 9. Okay, so we have differentiate the function y equals ex plus 2 plus 1. This one's kind of interesting. So we're going to use this fact. If I have x to the a times x to the b, that's the same as x to the a plus b. We're actually going to go the reverse direction. We're going to go this way. So when we have y equals e to the x plus 2, we're going to write that as e to the x times e to the 2. So I'm just using this idea that if you're adding powers, it's basically like taking the same base times itself with where each base has one of those 2 powers. So ex plus 2 can be ex times e2. But e2 is just a number, it's a constant. So I'm going to write this a little different even more. I'm going to write this as e2ex plus 1. Okay, and then we know that the derivative of this, any constant in front of ex will stay. So e2 is a constant, so it's just going to stay there. Then the derivative of ex is ex, so that's not going to change. And then the derivative of 1 is 0. And I'm betting they want us to write this back in the original form, so we'll write this back as ex plus 2. Okay, so that should be the derivative. Okay, and we've got that one right. All right, problem 10. It says differentiate the function s of r. So we have, looks like some kind of area function. So we have s of r, circular area, equals 5 pi r squared. The derivative of s prime of r would be bring the 2 down, so it becomes 2 times 5 pi, and then it becomes r to the 2 minus 1. So this derivative will be 10 pi times r to the first power. And that is going to be it. Should be pretty quick and easy. Let's see, how do they do pi here? Times r. And you can just write r to the first as r. Don't even know if I need those times in there. Let's see. Yep, so that works just fine. Okay, that's problem 10. Problem 11. Oh boy, okay. Not too bad, it's just be a little bit of algebra. So we have 2x squared plus 6x plus 6 divided by, I'm going to write the square root, just to save us one step, I'm going to write square root of x is x to the 1/2. So square root of x is the same as x to the 1/2 power. Now it turns out that we can write this, we can break this into 3 different terms. So this is really y equals 2x to the 2 minus 1/2. So when you have x to the a over x to the b, that's the same as x to the a minus b. So I've got 2x squared over x half. Let's write that as 2x, 1 base, x, raised to the 2 minus 1/2. And then we're going to do the same thing with this 6. It's going to be 6x to the 1 minus 1/2. And then this 6 would just be 6x to the minus 1/2. Okay, so we're going to get y is equal to 2x to the 3/2 plus 6x to the 1/2, and then plus 6x to the minus 1/2. Okay, so now it's in a form that we can do the derivative fairly simply. We're just going to bring the 3/2 down and multiply it into the 2, and then it's going to be x to the 3/2 minus 1. Then we'll bring the 1/2 down into the 6, and then it's going to be 1/2 minus 1. Oops, I can write like that. Then it's plus minus 1/2 times 6, x to the minus 1/2 minus 1. These 2's will cancel, so you're going to get 3x, 3/2 minus 1 will be 1/2. So you get 3/2 minus 2 over 2. So you have 1/2. This will be plus 3, 1/2 times 6, x to the minus 1/2, when you subtract 1 from 1/2. And this will be minus 3x to the minus 3 over 2. And let's see, they probably want this like this. 3 times the square root of x plus 3 over, so x to the minus 1/2 is really the square root of x in the denominator. And then we'll have minus 3 over the cube root of x squared. Nope, I wrote that wrong. It'd be x cubed. The 2 would go out here, but we don't usually write 2 in front, so we're going to call it just the cube root of x. Okay, so let me type that in and see if that's what they're looking for. Okay, so if we look at the answer I typed and what I wrote, it is true. You do not have to write this 2. It's not incorrect, but we don't usually write it. So this 2 I did not write here because it's understood. So it's understood that there's a 2 in front of this square root. And so we don't have to actually type it for the final answer. I bet if you typed it, you'd still get it right. But if you follow this, just do it the way I do it, and you'll get it right anyway. Okay, problem 12. Okay, so we have g of r is square root of r. Capital G of r is the square root of r plus the 6th root of r. Well, we're going to write that as fractional powers 1/2 and 1/6. And then we can immediately do the derivative, which would be 1/2 r to the 1/2 minus 1 plus 1/6 r to the 1/6 minus 1. And when we simplify that, we get 1/2 r to the minus 1/2, and we get 1/6 r to the minus 5/6. Well, we're going to then write this as 1 over 2 square root of r plus 1 over 6, the 6th root of r to the 5th. And that should be the answer for that one. Okay, that looks good what I've typed there, but they want a second step where they want the second derivative. So when we have one slash like this, that means the first derivative when we have two slashes, that means the second derivative. But the rules are exactly the same. So the second derivative, we just do this whole thing again, starting from the first derivative. So from the first derivative, we are now going to take a second derivative. So starting from here, let me do a different color so you can see what I'm driving at here. We're going to find g double prime of r. And it actually is useful to start from the unsimplified version, where it's still the negative fractional powers. So now we have minus 1/2 times 1/2 r to the minus 1/2 minus 1. Then we have, I'm going to run out of room here. Let me write it over here. Plus, this negative 5/6 will come down, multiply into the 1/6, and then it becomes r to the minus 5/6 minus 1. Let me see if I go down here a little more space. So g double prime of r is going to equal minus 1/2 times 1/2 will be minus 1 over 4. And it's going to be r to the minus 3/2. And then minus 5/6 times 1/6 will be minus 5 over 36. R to the negative 11 over 6. So if you take minus 5/6 and you subtract 1, which is really minus 6 over 6, you get minus 11 over 6. Then to simplify it, we'll write this as minus 1 over 4. It's going to be the cube root of r, I keep screwing that up, r to the 3 and then the 2 out front. We're not going to write the 2. Actually, I am going to write the 2 just to help you not do what I keep doing. I keep flipping the order here. The number on top stays with the r, so r to the 3rd, that 3 stays with r, so it's r to the 3rd. Then the 2 goes on the outside of the radical sign. Okay, then it's minus 5 over 36, and this is going to be r to the 11th with a 6th root out front. Okay, so that is the second derivative. So let's try that. Okay, and we have this one correct, so just notice that in the final answer, once again, I did not type this 2. So that 2 I did not type, but everything else I typed exactly how I wrote in this bottom right green line. So that would be the second derivative. Okay, so we're going to expand on this idea. You can take second derivatives, third derivatives, fourth derivatives. You just repeat these steps over and over again. So it says, show that the curve y equals 8ex plus 4x plus 3x cubed has no tangent line with slope 3. So no tangent line can have a slope 3. Okay, so the derivative, so let's start with y. So it says y equals 8ex plus 4x plus 3x to the 3rd. What are my actual options here? Okay, so they want us to take a derivative of this. So the derivative of 80x is 80x. The derivative of 4x is 4. The derivative of 3x3 is 9x squared. Okay, and they're basically saying let me actually go to Desmos and plot this, and then we'll see why they're saying what they're saying. So basically, this is the derivative, and we're going to say y can never y prime is always bigger than 3, so you can never have a tangent line that has a slope of 3. Well, let's prove that with the derivative. Okay, so I've graphed them both in decimals. So I've got the original function 8e raised to the x plus 4x plus 3x cubed is in red. So it's kind of interesting. It looks like a straight line. And then the derivative, 8 exponent x plus 4 plus 9x squared, is this blue line. Well, notice that that blue parabola shape is always above 3. So 3 is all the way down here. Let me mark this up. So 1, 2, 3. Here's 3. Notice that this derivative is always above it. So the derivative starts at around 9-ish, or not 9-ish, almost 11, and then just keeps going up. So you're never going to get 3 from this. The slope of the tangent lines will always be bigger than 3. Okay, so let's go back and answer that. Okay, and the way we answer that question is we write in the derivative, which I had written on the screen before, and then we put y prime is strictly greater than 3, so no tangent line can have a slope of 3. And that's problem 13. Problem 14 states, find the points in the curve y equals 2x3 plus 3x squared minus 12x plus 2 where the tangent line is horizontal. Okay, tangent line is horizontal. That is saying the derivative is equal to 0. So we have to find, so y equals 2x3 plus 3x2 minus 12x plus 2. The derivative, we'll get pretty fast with this, is 6x squared plus 6x minus 12. The x goes away, the 2 goes away, these powers came down and multiplied the numbers in front, and we decreased the powers by 1. Okay, now we're going to set that equal to 0. So we're going to say 0 equals 6x squared plus 6x minus 12. Then, just to make my life easier, I'm going to divide everything by 6. Shrink those numbers a little bit. Because I'm going to have to factor this, 0 divided by 6 is 0. 6 divided by 6 is 1. 6 divided by 6 is 1. 12 divided by 6 is 2, and it's negative. So this will factor into plus 2 minus 1. So the last two terms will multiply to minus 2, and they add to positive 1, the number in the middle. So that is the factorization of that quadratic equation. And this causes, these will cause x to be 0 when x is negative 2, or when x is positive 1. So these bubbles will go to 0 when x is minus 2 or x is positive 1. So we then have to plug in, so it says the smaller x value. The smaller x value is negative 2. And the larger x value is positive 1. But they want the actual xy coordinate. So we have to plug those x's back into the original formula. So we have to plug x equals minus 2 into the original formula, 2x cubed. Instead of x, I'm going to write minus 2 cubed plus 3 minus 2 squared minus 12 times minus 2, and then the formula says plus 2. Let me at the same time write the positive 1. Positive 1 is nice because all the x's are just going to become 1. So this is just literally going to be 2 plus 3 minus 12 plus 2. So I hope you can see that. If x is 1, x cubed, which is 1 cubed, is 1. X squared, which is 1 squared, is 1. So all the red numbers are just going to stay around and all the x's will leave. So this is going to be, let's see here, we got 5, 7 minus 12. So it's going to be negative 5. And then over here, we got a little more work to do. This is going to be negative 8, positive 4, positive 24 plus 2. This is going to be negative 16 plus 12 plus 24 plus 2, and all that equals that is going to equal positive 22. So we just have to type those in, but we have to make sure we get them in the right spot. When x is minus 2, the y value is 22. And when x is 1, the y value is negative 5. So just be careful, you're plugging those numbers into the original function, not the derivative. If you plug them in the derivative, you'll get 0, because we proved at those x's the derivative was 0. Or at least if we got it right, they should be. Okay, last problem. Find a second degree polynomial p such that p of 2 equals 1, p prime of 2 equals 3, and p double prime of 2 equals 4. Okay, here's how we do this one. We set up a general problem. So we have y is equal to ax squared plus bx plus c. And actually, let me not use y because they want us to plug in numbers. In fact, they told us p, so let me use what they used. So they're using p of x. Well, p prime of x has to equal 2ax plus b, that's it. P double prime of x has to equal 2a. Well, we're going to work backwards. So this says when p double prime, when you plug in 2, this should equal 4. But notice x isn't even there anymore, so it doesn't matter what x is. This says that a has to equal 2. So basically, these two have to be equal. Therefore, a must equal 2. Okay, now we can start to back substitute and solve. So let's put a as 2 in there. So now we know p prime of x is really 2 times 2, which is 4x plus some unknown variable b. But then they tell us if you plug in x is 2 again, the whole thing should be 3. So the whole thing should be 3 if we plug in x is 2. So we get 3 equals 8 plus b. Subtract 8 from both sides. Minus 5 should equal b. Okay, so now we're going to use that and the fact that a is 2. So we know a is 2 and we know b is minus 5. And we're going to plug those into the final form of the equation, the original form. So p of x has to be a, which is 2, x squared, plus bx, which is really minus 5 times x, plus c. And the last bit of information says when x is 2, the answer is 1. The whole thing becomes 1. So this whole thing becomes 1 when x is 2 again. So we get 1 equals 2 times 4 minus 10 plus c. We get 1 equals 8 minus 10 plus c. 1 equals minus 2 plus c. Add 2 to both sides. C is 3. So we plug all of that in and we would say p of x has to be 2x raised to the second minus 5x plus 3. And we get it right. And that will conclude Chapter 3, Section 1.